Welcome back to learning about acids and bases, and get into a little bit of another reason why water is my favorite molecule. In the book, you'll read some different definitions of what an acid and a base is. These three gentlemen have some different definitions, some different ways of thinking about them. They're really they all mean the same thing, but it's sometimes good to hear these definitions, because you'll definitely probably hear them if you take a college chemistry class. Arrhenius was the first gentleman. Basically, things donate hydrogen when they're in aqueous solution in water. Bronsted-Lowry is kind of similar, but kind of think about more about the thing taking the base, taking the hydrogen. And then you have the Lewis definition, which really gets more into some things where you have bases that don't have hydroxide, which do exist. So you can read about these. I'm not really too concerned about memorizing these definitions or anything, but kind of look at them a little bit here. Acid supply, protons, or this H+, which is called a proton, and then you have, or hydronium, as you'll see, and then bases supply these OH minuses, these hydroxide ions. Here's a Bronsted-Lowry with a chemical reaction here showing what happens, right? You have to the left, you have your reactants. Here's just generic H with some ion, right? Plus water. It has to be in aqueous solution. It's not an acid unless it's in water, unless it's in an aqueous solution. So you have this generic H plus some anion, okay? And here's the arrow to the products on the right side, where this has now given away its proton. So now it's just A minus. Now it's just the anion, the charged ion, negatively charged ion. Here's water that's with the HA, and so it's taking that hydrogen, becoming H3O technically, and that's actually not even, that's just a simplified version of and we'll actually simplify that even more. Okay, so this is the acid on the reactant side. This is the base on the reactant side. Opposite, its pair, right? It's called the conjugate pair. This is now the base, right? Because this reaction could go both directions, right? So that you can see the yield sign is not one just to the product side. It goes both ways, and it's dynamic. And then here's the conjugate acid. And so this, if you think about this going the opposite way, right? This is the conjugate acid, because going the opposite way, it's the acid. It's the one giving the H away. Right, and this is the conjugate base, where it's now taking that. If you're thinking about going the opposite direction, that reverse reaction. So those are the conjugate pairs. It's pretty easy. That's a lot about in the book, but you want to just note some things here. As you can see, the conjugate base remaining after the proton is lost. The conjugate acid is what gains the proton, so they're just kind of opposites. But here, note, the anion has a stronger attraction for the proton, then it's going to be farther to the left. Okay, that means that this conjugate acid here, right, if it's attracted to the stronger attracted to that proton, then it's going to be more to the left. This reaction is going to be more to the left than to the right. So you're going to have higher concentration of reactants than products. Okay, that goes along with that acid constant, which is the Ka here. So we talked about that constant in the last video. When you're talking about what the concentration of the acid is, this is the Ka. Okay, you can also we can also have in terms of, you can talk about this in terms of how strong of a base something is as well. So this is the acid constant. You can also have a base constant, right? So you're looking at the how much of the base, what the concentration of the base is, and they're pretty much the same thing, or they're actually opposites of each other. So I'm just going to introduce this. So you can also have the Kb, which would be the this is the acid dissociation constant. This would be the base dissociation constant. Okay, and so it'd be the Kb would be, since we're talking about acids and bases, here's the equation, right? Remember, these brackets mean concentration. So the concentration of the H3O plus, which we actually, this is a simplified version of what's actually happening. We actually simplify that to this even more. We just say it's the proton, right? Because it has that extra proton. These are the same thing, okay? H3O plus, we simplify that to H plus. We don't have to write the 3O, right? Simplifies it a little bit. And so you can see here that, move this a little bit up. Where this comes from is, of course, from this reaction here. I wonder if I can take this, yeah. So I'm going to put this down here so we can look at both at the same time. So here's the reaction. Hello. Sorry. So the reaction is there. Okay, and so we have our generic HA, okay, that's plus our H2O. Okay, we leave that H2O out because we're not worried about the concentration of that. You can see we can simplify it even more. So we have our concentration of the reactants, just our HA, and on the top, we leave out the water. On the top, we have, there's water on both sides. There's water everywhere. This is all aqueous, right? On the top, we have the concentration of our products. So we have our H3O plus, H2O plus, simplified to HA, and our anion concentration of those. If you think about that, let me just point this out first. For every one of these acids that dissociates, right, you're going to have one each of these. These are always going to be in the same concentration. Right? These cannot be different because they both come from, they're dissociated, they're a product of your reactant here, your HA. So for every one of these, you have one each of these. Okay, so the concentration of these are going to be the same. That'll come in handy when we're trying to calculate some of this stuff. Okay, so we think about these acid dissociation constants here, this Ka. If it's bigger than 1, right, think about this mathematical equation here. If it's larger than 1, that means the numerator is bigger, right? And so you have more reactants than you have more products than reactant, right? So that favors the products if it's larger than 1. If the acid dissociation constant, the Ka, is less than 1, right? That means you're dividing by a larger number. Your numerator is larger, which means you have more reactants than products. So that favors the reactants, okay? Here's an example of acetic acid. I think you saw this yesterday. This is a weak acid. Okay, it's where you have, this doesn't dissociate completely, so you will have a lot more reactants than products. And so this is an example of a very small Ka acetic acid is. Here's just a little demonstration. This is why they have the Lewis acid concept. This electron, the perfect example of that is ammonium. Okay, so you have your H plus, which would be H3O, or which would be H2O, comes from the H2O, plus your ammonia ion. This is what it looks like. You have this lone pair of electrons, right? Perfect for something that's positively charged, like a proton. So it adds to it, and so here's your Lewis acid donating. Here's your Lewis base, right? It has that electron pair, so it takes it and makes this. That's just an example of the Lewis base concept. It's in your book. Now this is kind of the cool part here. Water. Why acids have to be in water, right? We've learned all about water, and it's amazing. It's a polar molecule. It can donate hydrogen atoms. It can take them, and when we can do both, when something has the ability to be both an acid, either an acid or a base. Okay, this is what we call amphoterism. Water is amphoteric. Okay. That means it can donate a proton or it can accept it, right? It has a proton to donate. It has two lone pairs. If you remember the water molecule, what that looks like, it has, so it can donate a proton or it can accept it. Okay. And so what happens is, and this is why water is wet, water can actually ionize in itself. Water dissociates in water. Right, so we talked about this last semester jokingly that, oh, well, couldn't we put this water molecule as aqueous? We sure can. This is why water is so amazing. And this is why water is wet. It actually donates a proton to another water molecule. Okay, it actually dissociates in itself, making a H3O and an OH minus. Okay. Water actually ionizes in itself, dissociates in itself. So it can act as an acid, as a base, conjugate acid, and a base, H3O, OH minus, okay? It can use a lone pair, it can, or can give a lone pair, can use a lone pair. It is amphoteric. It is both an acid and a base at the same time. It's amazing substance. Those are the definition, the three different definitions showing you there. Okay, so this water molecule gives its hydrogen to this water molecule. This is the acid, makes us the acid. This is the base, changing it to H3O plus and OH minus. This next little part here, this might be some reading, but I'll kind of read it here to you. When you think about this in solution, right? And we've seen this diagram here before, where when you have a water molecule, here's a picture of the water molecule. Excuse me, right? Partially positive on one side, negative on the other. It looks like Mickey Mouse. You have something like salt, okay? And what happens is the polar molecule breaks this bond, having this would be sodium chloride. You have sodium making this kind of like bubble, or this, what's called a cell around it, right? The same thing happens with the chlorine, but now the hydrogens, the positive ends are pointed towards chlorine. We've seen this before. But the amazing thing is that water does this in itself. And so you can imagine this not being water here. Let's say this is, let's make this, cover this up here. We can put this, I'm doing on time, almost done here. We can put a water molecule in here, right? And so this H plus, I'm just going to write it. This H plus gets surrounded by all these water molecules. It actually, right? And then you have your OH minus here, which gets surrounded by the water molecules in the other fashion. Here would be a OH minus in here, right? So it actually dissociates in itself. This is why it's wet. It actually sticks to itself. OH minus. Makes these cells around other water molecules. It's pretty amazing phenomenon, pretty amazing substance. And let me just put this here, and you can pause it. Whoops. You can pause it to the end of this and just read through this statement here, because it's pretty amazing what happens here.